Okie dokie. So, this class, CS124, is a detailed, somebody mentioned on Facebook, you say introduction to in all of your classes, Caltech, and this is a very valid accusation, probably something we need to address. But it is a very detailed introduction, and I love it because by the end of this class, you'll be so familiar with so many different aspects of operating systems that you'll really have a very complete knowledge, and that's pretty neat. There is a hard prerequisite of CS24, particularly the last half of the course where we actually talk about operating system issues, operating system implementation details at a very high level, sort of the services that they offer and so forth. So that's why CS24 is a hard prereq. If you're an undergrad and you haven't taken CS24, you should be scared. I will probably make you drop it. I will probably force you to drop it. If you're a graduate student and haven't taken CS24, I'm a little bit more lenient because obviously you were probably an undergrad somewhere else. So you need to be clever and evaluate whether or not you have had equivalent experience. And this is a project class. This is one of those classes where if you haven't developed a certain level of coding maturity, Mike and I like to call it, then it will be a very challenging class for you because you have a ton of code to understand, and then you have a significant amount of code to write. And it probably is going to be more challenging code than most of the code that you've written so far. If that doesn't describe you, then good for you. You'll probably have a good time solving the fun and exciting and challenging labs. But it is very challenging because of the amount of code to digest and the amount of code that you have to create. So like I say here, the majority of the programming is in C. A small amount is in IA32 assembly. Approximately 10% of your class will probably be devoted to IA32 assembly because one of the assignments you'll have to write more than a little, but not a lot. And we'll use Git for version control. There are two things. One is that it will help you to work with your teammates, and the other thing is that it'll allow me to retrieve your submissions and then grade them. And obviously, if you're familiar with Make, great. If you're familiar with Doxygen, I have Doxygenized basically all of the Pintos code so that you can generate documentation for it and follow links into the code. So there's some things I've been working on to try to improve the code base beyond what it sort of came to me as. And so if you're familiar with these tools, it'll definitely help. No exams, my favorite kind of class, because I hate exams as much as you probably do, maybe even more because I have to write them. And then I also have to solve them, so that I have to actually know that the questions are good. And so the grade is taken entirely from the assignments. And about the last, I should say about 80% of the course is actually based on this instructional operating system called Pintos. There's probably 4 or 5 different instructional operating systems. And Pintos was developed at Stanford for their CS140 class. It's a very well-known class among people who like operating system classes. And it's used by quite a number of schools, actually. I'm not going to try to enumerate them because I don't remember offhand. But it's neat. It's x86, which all of you, if you've taken CS24, are familiar with IA32 assembly language. There's a number of them that are designed for MIPS. It's like, who here knows MIPS assembly language? Okay, so that's even less than I expected. There's usually 1 or 2 grad students who say, yeah, I had to do MIPS programming when I was in undergrad or something like that. So pretty straightforward. It's great. It's very simple. It basically has everything that is necessary and not much more. So it's a really good starting point. Now, I'm going to go ahead and give a little sales pitch, too. One of the things that I would like to do is if you really love this material, and besides wanting to be a CS24 TA, you just can't get enough, and you say, I'd love to do a personal project in operating systems. I would like to suggest you consider CS81 as an option, perhaps writing something on your own or writing something as part of a small team. One thing that is very interesting, there's a new language called Rust, which probably many of you are generally familiar with, and is supposed to be good for systems programming. And I would love to see if somebody would like to, for example, try writing a microkernel architecture operating system in Rust. Perhaps that could be the next generation of our instructional operating system that we actually use for this class. So something to consider. Obviously, that's 10 weeks away. You may think you love operating systems now, and in 10 weeks you're like, That's it. I'm going into show business. Or fast food, which whatever it might be. Anyway, all of this stuff is going to be on Moodle. Basically, assignments will be posted there. Slides will be posted there. Obviously, we're going to be recording everything so that you can go back and watch them, because they're very exciting lectures. I watch them all the time myself because I'm just so mesmerized by my own voice. But you can go ahead and sign up for the Moodle course. If you have your computer and your board, do it right now. The enrollment key is K-Thread, if I did that correctly, which is not similar to K-pop. It means something else. So, yeah, and basically I'm going to start using that for announcements pretty quickly. So probably by Tuesday or Wednesday, I'm going to start using Moodle to start announcing things. So just get signed up as quickly as you can so that I can actually let you know things. Now, there's 2 books, which I already mentioned in email, so I'm not going to spend too much time on this, but they are completely optional. Books are so freaking expensive, it makes me really upset. Especially, I mean, I get them for free a lot of the time as a teacher, but it still frustrates me because you're it feels like taking advantage of people when you have students who don't have an income and you're like, okay, yeah, you only have to pay like $930 for this book. So, I generally try to make sure that they're optional for my courses. So Operating System Concepts is a really good book. We follow loosely a lot of the material in this book, and you can see that one of the authors is actually the same as the Database System Concepts book, so Silberschatz is the same. He worked on both books. But it's very high level, and one of the things you notice is that most of the time the devil is in the details. So high-level coverage is nice, it exposes you to the concepts, but it doesn't show you all the real nitty-gritty details you have to get into. Then there's Understanding the Linux Kernel, which is like my favorite book of all time when it comes to understanding operating systems, because it actually goes through all of the details of how Linux works, and it probably covers the vast majority of the kernel source code and explains how all the different mechanisms work. And it's a very detailed book. You know, even me, I've been programming for nearly 30 years now. Is that right? Yeah, it's been a long time. And I have to read sections in this book multiple times just to make sure that I actually understand all the details of what's going on. But it's a very, very deep book, very valuable. And since Pintos follows Linux architecture pretty closely, not super closely, but closely enough that there's a strong similarity, I think that it is very helpful to have a copy of that book available somehow. Okay, so like I say, your teams might want to get access to the book. I will try to give you reading pointers to the second book because it's really nice and helpful, but there's no assigned reading. If you decide you don't want to get these textbooks, that's perfectly fine. I think you'll be able to do the class perfectly well. Okay? See, assignments. So there's 6 assignments, and we're going to start with the first assignment on Wednesday or Thursday at the latest. It'll go out. Write a basic operating system shell. It's kind of a hey, this is systems programming type assignment. It seems challenging until you get to the later ones. Second one, write a bootloader, and then you have the Pintos assignments. You do kernel level threading, thread scheduling, system calls, so you get to start understanding the separation between kernel mode and kernel space and user space, and the various details around that. Virtual memory system, which is kind of scary because they say implement virtual memory for Pintos in this directory, and you go into the directory and it's empty. You're like, oh man, this is going to be a long 2 weeks. So, and then the last thing to do is to extend the file system. Pintos comes with a file system, but it's fixed extent and it's continuous extent file system. So files can't grow and they can't be sort of spread across the disk in multiple sections. And so you'll implement something like Linux's ext2 file system format. Okay, so that's basically the lay of the land. What you'll notice, if you do the math, and it's complicated math, is that the assignments end up spilling into finals week. So I guess you can sort of consider the file system to be your operating system class final. Yay. But anyway, it's pretty straightforward stuff. I don't think that it's going to be too terrible. And obviously the 2-week assignments will be worth more than the 1-week assignments. All right, so that's straightforward. The assignments are hard, and I I don't want to oversell this, because sometimes when you tell students this stuff is really hard, they carry that into their minds and they're like, I'm going to have a real difficult time doing this. Honestly, operating systems are glorified bookkeepers. That literally is all they do. The part that makes them challenging is that everything happens all at once at the same time. That's the part that makes it challenging. But it is just a big glorified bookkeeper. So it's not like conceptually it's hard to understand. There's parts of it that are. It's just that there's a lot of things going on and you have to think it through. And so that's the part that makes it hard. I don't want you to get scared off of it. So what I do is I require you to work in groups of 2 to 3 students. And it's not that people can't do it by themselves. People have done it by themselves. But the number one issue, do I mention this? Yeah, is that you'll have somebody to talk to about debugging, which is so helpful. I was really astonished at how big of a difference it made to have other people to talk to through bugs. Because a lot of times it is, blah, 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 I have this issue, and oh, that's the problem. And you realize and you go, and in fact, I think there's a technique called, like rubber duck debugging, where you have a rubber duck on your desk and you describe the problem to the rubber duck and then you realize what the problem is. So, and that way you don't bore another human being. But, it's nice to have somebody else to talk to about this stuff. So, of course, we encourage you to think very carefully about whether you are going to commit yourself to the entire course, because if you decide to drop it will affect other people. I'm going to try to manage this as actively as I can this term. So, I don't want anybody to think I have to not drop this course, even though I've got an F minus and, I'm already on verge of getting UAShed or whatever. We'll figure something out, okay? You should drop a class if it's really bad for you. But I do want you to think about this ahead of time more, because it does affect other people. Okay, yeah, and we will be able to adjust teams if necessary. Okay, so I mentioned Git. I'll create those repositories on the CS cluster. And I don't care if you work in another Git repository. A number of people seem to like working on various public Git hosted Git systems, which is neat. It's neat because you have things like bug tracking or other things that are provided by those systems. I just need to make sure that your code makes it into the repository that I create, so that I can actually, grade it. Now, I say here I give you the code base for the course as part of the first assignment. That is probably an overstatement. What I will do is I will give you some portions of the code base, and then I will give you the bulk of the code when the third assignment rolls around, because that's the first real Pintos assignment. I don't want you getting bogged down, distracted with other things, so I'll probably start with something small, and then we'll grow it from there. But once you set up a Git remote, you can just pull from it any time, and it'll all be cool, so you won't have to worry about that. Okay, so honor code, collab policy now operates at the level of teams, not at the level of individuals. So teams must create their own submissions. They can't share implementation code, but you are strongly encouraged to share other things like ideas and debugging help. And wow, I tried this and my computer exploded, so don't try that yourself. Okay, things like that would be incredibly helpful. In fact, I typically set up a piazza to help with this class where people can go and post questions and so forth, and then other people who have figured it out can help. I might actually do some kind of point bonus for that kind of thing so that we can encourage collaboration more. So I'll have to sit and think that through. Anytime you create an economy, you have to make sure it can't be gamed very easily, so you have to think about that stuff. Also, Pintos has been around for, 10 years now, so please don't go look for solutions online. I would really like you to not do that. I think that's all I'll say about that. I think it's just obvious. But the other thing is that if you decide to go jump into the Linux kernel or Linux operating system implementation, I'd be happy for you to do that. I look at that stuff frequently when I'm trying to figure things out. And it's a really good idea to go look at some sophisticated working implementation to get ideas. So don't copy code. You need to understand it. And I have in the design documents a section where you cite external sources. Because if it's a really good external source, then I'm going to share it with everybody in the class. I want to make sure that that kind of information is shared. So, but don't copy code. If I discover that you're copying code, then it's going to be, I'm probably going to be in my office crying. and then we'll have to follow whatever process there. So anyway, just make sure that you understand what you do and create everything yourself. Assignments and due dates. So Thursdays at 2 a.m. I don't know why. It's just what I've settled on. So that's what we'll end up doing. Late penalties are typical for my classes. So 1 day late is 10%. I don't care if you're a day late too much. 2 days late, and if it's like 1 day late and you're answering a ton of questions on Piazza and I figure all that kind of stuff out, then it probably will all wash out to be exactly the same. 2 days late, it's compounding. That's probably the wrong use of compounding, but 3 days late and so forth. You can see that after 4 days, it is too late. Teams have late tokens. This is always an interesting situation. Teams have late tokens, so you have up to 4 that you can use. No questions asked. And of course, students can also request extensions in various other ways. So, look, Donnie, I'm deathly ill. The health center said I almost died 4 times in the last 6 weeks. Can I have an extension? Sure, if the health center said. Dean's office, sometimes those are a lot more serious situations that might arise, but we're perfectly happy to accommodate those things. It's a challenging thing to figure out. One student in a team decided, I shouldn't say decided, they decided to get sick. One student in a team got sick, and obviously that affects the whole team. So I need to figure out exactly how to grant extensions in that situation. That's an area that is unclear to me at present, but we'll iron those situations out. Okay? Let me see, is there anything else? Okay, let me just ask, are there any logistical questions right now? Because I think that's the bulk of the logistics for the class at this point. Anybody? Yeah. How are teams getting made? Through a complex process that is a mystery even to me at the moment. But no, the idea is that everybody has this survey that I sent out. I want you to fill it out and say, these are people that I would like to work with. And then what I will do is write a program to solve the matching problem of trying to figure out who should be paired with who. So obviously, if you say this is the team that I would like to work with, then that is probably going to be your top priority as far as who you actually get to work with. So what I'm hoping is that I will get to tweak things and I won't have to generate things from scratch. But there's always people in these classes who don't know very many people and they don't know who to work with. And so I want to try to use the other questions in the survey to try to place people properly. So that's the idea. And I have no idea if it's going to work well, because this is an experiment, as I told you. Okay? So if you have any ideas or concerns about that, please share them with me in email, and I will be happy to take that into account. Yes? I'm going to try to make sure you know your teams by Wednesday. So obviously that means I need people to fill in their surveys as soon as possible. I've gotten probably 12 and a half, so I need more. Yes? That is correct. Yes, you can email it back. I would love to have an actual online survey or have you send me properly formatted JSON data, but I thought both of those were probably too much difficulty, so I said just send me back the text file. Yeah. Any other questions? All right. Thank you for being my guinea pigs, and I hope it isn't something you regret. All right. So Pintos is designed and implemented to be built and run and exercised on Linux. It all runs in an emulator, so it's not like you have to have a special machine for it. The very first time we offered this class, 2 students sat down and actually figured out how to get it to run on OS X, and I was quite amazed, and they sent me the instructions, and I said, no one will ever do this, so I burned them. So, but there's a lot of interesting nuances. Processor emulators are actually surprisingly dependent on their host platform because they do rely on emulated services provided by the host platform, and so that can definitely have an effect on how they behave. And so I want you to have something that is as uniform as possible. And so I'm going to be testing on 32-bit Mint Linux, which is what I've been developing with for this class, and it's what I will give you a virtual machine with this Linux. If you hate Mint, I'm sorry. You can figure out how to set up your own 32-bit Linux platform. It is super simple. I just picked Mint because I wanted something simple and not horrendously heavyweight. So that's why I picked that. But yeah, if you want to do some other Linux platform that's your favorite, that's fine. It just should be 32-bit. Okay. So yeah, I'm getting the virtual machine set up for you right now. There will probably be various little details that need to be ironed out through the progression of the course, but I'll just send emails to the class when those things need to be done. But I'm getting it set up with all the tools I think you will need right now, and probably even a few more. For example, a number of people, who here is familiar or has heard of Bison and Flex, aka Lex and Yak? Okay, so command shells are pretty straightforward except for one annoying thing: parsing the freaking command line. So a lot of people hand write that, and there tend to be a number of bugs in those areas. Some people write them with a Lex and Yak equivalent. So you're certainly welcome to do that if you wish. So that is an example of a tool that's on there, and I think it's only needed for assignment 1. Okay. The Pintos testing code relies heavily on Perl. I hope that is the only way we'll ever need Perl in this term, is to run the test suite. So things like that. Okay, any questions? All right, that should also be available by Wednesday. Interestingly enough, you can write a command shell entirely on whatever Linux or even on Windows platform you would like, but then you notice that there's certain system calls that are slightly different on different platforms. There's various other things that vary from platform to platform. So I want you to at least test your submission on Mint Linux or on some other 32-bit Linux platform, because I definitely know that Linux and OS X vary in what they offer. So keep those kinds of things in mind. I mean, this is the world of systems programming. Welcome. It sucks, okay? What else can I say? Also, last detail before we dive into some other sort of background material is that you'll notice that all the way through we basically spend most of our time talking about how Unixes do it, or Unixin they sometimes say. So primarily Linux, but I don't want you to think that this is some kind of, oh yeah, and I wanted to also, this is a terminology point, that when we say Unix, I don't mean SCO Unix, SCO being the most annoying company ever, but there's a whole family of Unix-like operating systems, and OS X definitely falls into that category because OS X is actually based on a microkernel architecture that was developed at CMU, if I remember correctly. We'll talk about that in the future. But this is the thing I wanted to say. These concepts appear in virtually all operating systems, and Unix is just, or I should say Linux and these kinds of operating systems are just the easiest to experiment with because they were kind of designed to do that, and they were, they're made widely available, so it's easy to get something to experiment with. As an example, I'm definitely, there's things that Windows sucks at. When I talk about the Windows process scheduler, it's like, why did you do it this way? But then there's other things, like Windows has a really innovative threading implementation now, like starting in Windows 7, I believe it was, or in Windows 8. I can't remember offhand. But Windows does something that is completely innovative that you don't see in virtually all other operating systems. So when we get there, I'll talk about that. They all have strengths and weaknesses. Okay? So it's a great place to leave ideology behind and just sort of focus on, well, what are actually good and bad aspects of all of these systems. So I don't want to be somebody who's a fanboy, unless there's real reason to. Okay, what is an operating system? How would you describe what an operating system is? Large, complex. I like sophisticated bookkeeper, but there's a purpose behind it, so that's not a very good explanation. Yeah? It controls access to the system's resources. That's a really good answer. That's about half of what an operating system does. It controls access to the system's resources. What else? Any other ideas? Okay, well, that was a really cool answer. So, did you have an answer? Or idea?
Yeah, it exposes the system's resources to the end user.
Yeah, I like that one as well. It exposes the system's resources to the end users. Those 2 points actually capture 99% of what operating systems fundamentally are responsible for doing. Great answers, guys. Most generally, operating system provides applications with a standardized interface to the computer's hardware resources. We'll talk about why you need a standardized interface, but you can probably already, if you've taken 5X, you know. But, it's just the reality that there's all kinds of disparate pieces of hardware involved. The other part, the operating system manages the allocation and sharing of hardware resources to applications that want to use them. So this is sort of the governing side of things, that the operating system has to control who's allowed to access what and when. And there's tons of variations under this theme. So we're going to spend a little bit of time at the beginning of the class exploring these topics. What kinds of devices the OS runs, how the OS is architected. I mentioned microkernels. That is a particular architectural pattern in operating system implementation. And what other facilities, services, and guarantees the operating system provides. File systems are a great example of this, because we have all these different kinds of storage media that you can plug into a computer. What are some examples? I've got like my USB spinning magnetic rust bucket that I plug into my laptop every 10 days when it nags me about having not backed it up recently, and so I plug it in. So that's an example of a storage device. What are some others? Yeah. NAS, network attached storage. So that's a really interesting one because I actually access storage through the network. What are some other ones? There's tons. How about just connected directly to the computer? Yeah, flash storage. So you have a couple of different kinds of that. You have solid state drives. You have little memory cards, SD cards. Like I have a little SD slot on my laptop. You have USB flash drives as well. Something else, something spinning. Optical discs. I mean, how many people have computers without optical discs now? Yeah, it's becoming more and more. I like get a CD and I'm like, oh wait, where do I put this? Okay, I guess the microwave is it. So, but you have all these different kinds of devices that you can have plugged into your computer. And of course, we haven't mentioned internal hard disks, RAID arrays, which are frequently exposed as single storage devices as well. So, and this is just hard disks that I have on this slide. So parallel ATA. Does anybody have an IDE drive that they're actually using right now? Yeah, because I have a box of old drives too. But okay, so nobody has a computer with an IDE drive right now that's actually using it. Serial ATA. There's what is it? SAS now, serial attached storage, which I didn't include here. SCSI, which is becoming less common. SCSI is becoming less common, but that used to be really common for server systems. When I was a wee lad. USB drives that can be plugged in and unplugged. And of course, you have different things. You have sizes, and then you also have how old the device is, because we're starting to see variations in devices based on their age. So you had earlier disks that would use this rinky-dink mechanism, which was really great at the time, cylinder head sector addressing. This is what I grew up with, cylinder head sector addressing. It imposes this limit on how large a disk can actually be. We're going to spend some time talking about that in the future. But you also have this other issue that cylinder head sector doesn't actually reflect the disk layout anymore, because now, I have these zones on the outside of my platter which have more sectors than the zones on the inside, because I can fit more space. I have more space to fit data in close to the edge of the disk. So later disks introduced this thing like, okay, just give me a number, and then I'll give you the block that corresponds to that number. So that's logical block addressing, which can go much, much larger. They made the value that it takes much larger so that you can just access blocks very easily. And now the disk is responsible for doing that translation. But the OS has to figure out, okay, what do you need? And it talks to the drive and figures out what it needs to use to interact with it. You have different kinds of maintenance. I don't know if you think about that very often, except when your mom or your grandma calls us, my computer's slow, and you're like, okay, well, did you defragment the hard disk and all of that kind of stuff? Well, that's maintenance that the operating system has to deal with. And different kinds of storage actually require different kinds of maintenance. So magnetic disks, why are they sensitive to fragmentation? Yeah, because slewing a giant disk arm over the surface of the platter is slow. It takes milliseconds. And every computer that I know of gets really bored when milliseconds of time go by before it can get data. Okay. So that's slow, so we need to worry about fragmentation issues. Solid state drives, they don't care about fragmentation. But they have other issues. Anybody know what the issues are? Yes? Okay.
There's one, I forgot which one it is, but there's one combination of them that causes it to slow down by, at least 2x.
Okay, so writes, repeated writes, and then reads after writes. Those are good examples. These don't fundamentally get to the way that the solid-state drive works internally, which we have some lectures talking about it. So if you don't know, don't worry. We'll talk about it. Yeah?
You can read from a smaller section from then the amount you can write. You can only write to a whole block at a time. You can read from a smaller.
You're on the right track. You're really close. You're really close. The issue is that you can actually read and write to the same size blocks on a solid-state drive, but erasing is on a really large block. Once the block is empty, then you can write to it. But you can only erase really large chunks of memory in the solid-state drive. That's the issue here. So basically, we have a couple of different things that we need to think about. We have to erase blocks before they can be written to. So I write to it. I can't, it's very different conceptually than a hard disk, where I can just plop different data on top of the old data in the sector. In a solid-state drive, I've got to actually clear that thing, and then I can write something new to it. Okay, so there's an interesting issue there. And like I say, blocks can only be erased so many times before they wear out. So the operating system needs to interact with the solid-state drive in a very careful way to avoid causing issues. They also might have different file system formats. So there's a file system format, ISO 9660, which basically all optical drives use. And then you have the hard disk, and then you have the pluggable little flash drives, which are a different format. Most of them are FAT32 unless it's larger than 4 gigs, and then you have to use something else. So it's pretty common now. And then Windows and Macs have different file system formats and so forth. So there's all these things. So this is how Unix interacts with files. Open, close, read, write. And it doesn't care, I should say the application doesn't have to care what kind of device it is. Because the operating system provides this unified interaction mechanism for interacting with the computer. And there's a virtual file system where all of the things, no matter what kind of drive they're on or what specific drive they're on, they're all exposed in this unified layout that you can access very easily. Okay. I'm going to pick up the pace because we're getting a little bit behind. I get too excited about this stuff. Okay, now, let's say you want to open a socket. Or you want to open some other kind of like a pipe to another process or something like that. Well, it turns out that the interface is exactly the same. Open, close, read, write. Well, open is the part that changes. But close, read, and write are all the same. Lseek, if the device supports seeking, then that's available as well. The only real difference is how you open the device. And we'll talk about how these things are provided next lecture. But you can see how the operating system provides this unified abstraction to all of these disparate kinds of hardware. All right, does that make sense? Okie dokie. Now here's another one. Multiple processes can manipulate the same file. So here's a scenario. Process A opens foo.txt to read and write it, and then B comes along and decides it wants to delete foo.txt while A is still running. So what should happen? Different operating systems have different answers to this question. A lot of times Windows will just say, no, you're not allowed to delete this file. Does anybody know what Unix does? Yeah.
Doesn't it just leave it, kind of leave a weird ghost thing running until the last process looking at it dies?
You're very close to the right answer, yes. Yes. You're talking about an implementation detail that's actually not relevant to the conceptual, what is the model that it provides? Yeah. So the answer is, I'll just go ahead and give it to you really quickly, is that B is allowed to delete the file, and what happens is the directory entry is removed. The file data exists somewhere else on the platter, or on whatever device it is, and the operating system keeps a reference count to that data. And when that reference count hits 0, the data is reclaimed. So what happens is B deletes foo.txt, removes that directory entry, so nobody else is allowed to open it anymore, but A is still using it, so the OS leaves the data in place until A terminates. At the point that A terminates, the reference count of that data hits 0, the space is reclaimed. That's how Unix solves that problem. Is that the only right way to do it? No. It's just the way that Unix picked to do it. Okay? But you can see here that when you have hardware resources shared by multiple processes, the OS has to figure out how to solve these kinds of problems. It's the arbiter. That's why I really like, there's a description in the operating system concepts book of what an operating system is, and it says an OS is like a government for your computer. It doesn't have any inherent purpose to exist beyond giving programs an environment in which they can get work done. That's the same way a government is. Okay? I can't break into my neighbor's house and take his TV because the government will come and say, you're not allowed to do that, Donnie. So now my neighbor's allowed to live next to me without worrying when I eye his TV. So, same idea. So in Unix, so we already talked about this. Let's go back a little bit and look at the history of operating systems, because this will tell you basically why things are the way that they are. I find it really interesting. Basically, early computers were mainframes, and so you would have some kind of job that you wanted to perform, and it would be a stack of punch cards that you used to feed into the computer. And so you can see what the job actually contains. You start off, I want to run a Fortran program to process data. So the first part of that job was actually the Fortran compiler. And that gets loaded into the mainframe. And then you have the program, which goes into the compiler, and the compiler generates the machine code into the computer's memory. And then the data goes into the memory. Your program processes it, and then the output goes somewhere. So that was all done by a human operator. So the mainframe does its thing, and then the results are printed out on one of these old, like, or a daisy wheel printer. But basically, those really cool stacks of, like, accordion fold paper with, like, the little punchy holes on the sides. I don't know if any of you have seen that. I'm going to start getting to the point where I'm talking about technologies that no one has ever heard of in my classes, which will probably make me cry. But you can see that you're spending a lot of time waiting in the system. And we're talking about a very expensive computer. I'm waiting for the operator to put the cards in. I'm waiting for the cards to be read. I can't really do any computing. I'm waiting for the program to read its data. And then at the end, I'm waiting for the printer to print out the results. So the CPU is actually sitting idle quite a bit. So this is kind of what people did, is they said, how can I solve this problem of the thing being slow? And so they said, well, let's batch up jobs instead of just having a single job. So you'd have a simple computer that didn't cost very much, and the operator would sit and feed it cards, and it would write the data onto a tape. That looks very much like that one. Obviously, that's, well, actually on the slide it's about to scale. It's quite a large tape. And then the mainframe takes the tape, and it just reads the jobs in sequence and executes them. And then the results go to an output tape. So now you've improved the speed of the I/O. You don't have the operator sitting there getting in the way of the mainframe anymore, so that's faster. And you could also have certain tapes that were always present to have things like the Fortran compiler that everybody used. Okay? And then the output is, the tape is taken somewhere else and the output is printed. So this helps improve the speed that things could get done. But then they realized, well, there's another problem, because if one job is waiting to read data off of a tape, and it's got tapes are great for sequential access, but they're horrible for random access. And that's why we like disks so much, because they're much better at random access than tapes are. And so, the computer is basically sitting there waiting to seek until it can perform an I/O. And then complete the I/O takes time as well. So, what this introduced was this notion that, well, while one job is waiting to perform a task, let's switch to another job. So that's multi-programming. So, like I say, if the mainframe can keep multiple programs in memory, then I can actually get things done faster. You can see how all of this is like, how can I maximize my investment in this expensive large machine? How can I get things done faster? This was sort of the motivation all the way through. Okay, we're still in a world where a university would have one of these. So, or a company would have one of these. Now, what if you have multiple jobs running at the same time? Now you need to start sharing your computer's memory across multiple programs. These programs are not necessarily written all by the same person or team or company. And so basically you had to have some way of separating out each program's data and making sure that one program couldn't access another program's data. Okay, so this is the memory in the mainframe. And so we have to start providing process isolation. If we're going to have multiple things happening at the same time, and we don't trust them all to get along, then we need to be able to isolate them. So you can start thinking, okay, I remember CS24, process isolation, virtual memory. I have to have some kind of virtual memory abstraction. And then you also have to have some kind of operating mode differences in the way the CPU is implemented so that one process can't just change the mapping back to something else. The OS can have more capabilities and the jobs can have reduced capabilities that will keep them from causing trouble. Okay, does that make sense? So you see how this develops over time. Okay, the other issue. I carry my punch cards all the way across campus, and hopefully I don't trip and the punch cards go everywhere. There was an interesting thing. If you have a shoebox full of punch cards, what people would do is they would draw a line across the side of them, like at an angle or something, and that way, you drop all your punch cards, you pick them all up, you put them into the box, and you're like, oh, the line doesn't go like it used to, and so you can reorder them and put them into the right order so that you can do that. Obviously, if you draw a perfectly parallel line, you're going to be sad. That's not going to help you at all. But anyway, you take your punch cards, you give them to the operator, you go and, play racquetball for 6 hours, and then you come back and they say, okay, here's the output of your program. Syntax error. Great. So you see that debugging was very different in this world. You studied your program like crazy before you even took it over to run it because you had such a long turnaround to find out if something was wrong. So time-sharing systems basically allowed you to have a little terminal that was connected over a network to the mainframe. The terminal was dumb. It was basically keyboard and monitor. And it would connect to the computer, and you could type and do things. Okay, so you can see that this is an extension of multi-programming, and that instead of just having multiple programs, now I have multiple users. So this is where multitasking becomes a thing. I have process scheduling to consider, all of these kinds of things. I want to maintain interactivity, but I also want to be able to have compute-intensive processes run well. Okay. And it's interesting because the mainframe is still expensive, and if you had only one user, then you're wasting a ton of money because the user is the slowest thing that the computer's interacting with. But if I have a bunch of users all talking to the same mainframe, then I'm going to keep that CPU pretty well utilized. And there were all kinds of billing systems designed with that. I mean, there was just a ton of different mechanisms. Studying that part of computer history is actually really fascinating. I could point you at some books if you're curious about it. Okay, so you have integrated circuits. Computers get cheaper. Suddenly it's not tens of thousands or hundreds of thousands of dollars to buy a computer, so the whole company shares one or the whole school shares one. So now we start giving departments computers. So these are mini computers. If you hear that term, it doesn't mean like your watch or your laptop or your phone. It's a computer that's actually shared by a department or a group within a company. And then, obviously, this process continued, so you now have microcomputers where basically, it's interesting because now you actually have people interacting with the computer who don't care so much about how it works or how to program it or things like that. Now you have people who want to start doing things without actually understanding all the nuances of the machine. So this is where graphical user interfaces really started to catch on. They became necessary because mom and grandma don't want to learn C so that they can write their program to compute their recipes. They want to just use Excel or something like that. Okay. Now, graphical user interfaces. Does anybody know when graphical user interfaces really started becoming a thing? I love this stuff. So, none of us existed in 1960s. That's my guess. I think I'm right, yeah. I'm probably the oldest of all of us, and I didn't exist in 1960s. So there's this guy, Doug Engelbart, who, if you look on YouTube, you'll see this thing, the mother of all demos, and he demonstrates a graphical user interface that he created. It has a mouse, it has a graphical drawing program, it has a collaboratively edited hypertext system. You think that Google Documents is like amazing in the wave of the future. Back in the 60s, seriously. You have streaming video conferencing. All of that. He and his team came up with all of these ideas. So they've been around forever. And that's one of the things I love about operating systems is it gives you a sense of history. You know, I think, oh, I'm implementing this cutting edge thing. Well, actually, it probably was invented in the 60s, okay, or the 70s. Okay, so processors continue to become less expensive. So now we can have multiple processors in a computer. Remember, if you remember your last half of CS24, physics becomes an issue. We can't make them go faster and faster and faster. So we start adding more of them. So you have multi-processor systems. And the processors are in different packages. So now they have wires they have to communicate across, you know, out of one device and into another device. And then you have multi-core systems which put multiple processors in a single package. There's companies now where you can get, for not too expensive, 64 processors in a single chip, and you can program it to do stuff. And of course, I would say GPUs are another approach to the same thing, where instead of having like 64, 128 processors, you have a few, but they're very streamlined, very good at executing in parallel. And of course, having a multi-processor system requires OS support, because now the OS literally has multiple things happening at the same time. If you have a single core system, there's always only one thing happening, even though it looks like there's a bunch of different things going on at the same time. Once you have multiple processors, it becomes a lot more challenging. You should be thankful that Pintos is a single processor operating system. I wish I could have you work on a multi-processor operating system because it's so exciting, but then no one would probably ever complete the class. So anyway, of course you can continue this process. Well, now we can actually emulate. Processors are powerful enough to emulate processors on processors. It's crazy. So now we can actually run operating systems hosted in another operating system. So you can see that you have a host and a guest. You have two different approaches that you frequently see. You have emulation, which is where one CPU emulates a different kind of CPU. Anybody here been a Mac user for like ever? Like really long time? Do you remember Rosetta?
Yeah.
Rosetta was really cool because you have PowerPC programs that were written for OS X and blah, blah, blah earlier on, and you need to be able to run them on the new Intel Mac. How do you do that? Well, the instruction sets are completely different. So Apple provided a program called Rosetta, which would emulate a PowerPC on an Intel processor. And that would allow you to keep using all of your programs. It would be slower, but it would work. I thought that was so cool. And then you have virtualization, where basically you have the host and the guest actually run on the same kind of processor. So now the processor can actually provide hardware virtualization support directly to the guest to make it even faster. So now that everybody's basically a peer, although you have sort of a junior peer and a senior peer, running on the processor. Okay. If the processor's not capable of doing hardware virtualization, then you have to start relying on emulation again, which many virtualization environments actually are able to provide. So VirtualBox will probably be your friend or your mortal enemy by the end of the term. So that's an example of an emulator. It can certainly rely on hardware virtualization if you have it available. And it's becoming more and more common. So you're seeing this supported in hardware more and more. Now, you have that thing that sits and manages the guest operating system. We now call that a hypervisor as opposed to a supervisor. And it has mostly the same concerns that a regular operating system does. I mean, it's funny because it's kind of an OS for operating systems. It enforces isolation between guests. It manages access to hardware resources. Here, you can have this part of the screen and this part of video memory. Yes, you can talk to the sound card right now. Yes, you can have access to this USB device plugged into the computer, and so forth. But there are new challenges as well. If you think about it, you've got this guest operating system, and OSs have file system caching. They have ways that they interact with hardware devices to try to make the system fast. Well, now it's a guest in a host, and the host operating system and the guest operating system may have different ways that they want to manage caching. So this is something hypervisors need to take into account. Okay? So I don't think that's actually the this is the one that I was mentioning. So basically, the hypervisor has to find a way to keep the host from getting in the way of the guest operating system, in the way that it likes to solve problems. The other issue that I have here is that guest OSs expect to have access to hardware directly. So now the hypervisor has to find a way of providing this virtual interface that the guest OS expects to interact with. Okay? Just to touch on this issue, let's say that you're running an operating system and you want to change the page table of a process because the process's heap needs to grow. Okay? Some of you hopefully are remembering these details. Process's data segment needs to grow, so we change the memory mapping for the process, and now we start having page faults. A lot of this stuff actually involves touching protected mode registers. I'm only allowed to write to control register 3, which controls the memory mapping, if I'm the operating system, if I'm the kernel specifically. Well, what if the guest OS tries to touch that thing? Well, what happens is it generates a fault, and the hypervisor sets up something where it receives the fault, and then it can go ahead and it can either do what the guest OS wants to do, or you have some other interactions between these things. You also have the question, should the guest OS be able to tell that it's running inside of a hypervisor? Most of them can, okay? Because the OS is written in such a way, and the hypervisor is written in such a way that the guest can say, hey, am I in a hypervisor? And the hypervisor says, yes, you are, and they interact so that they can collaborate. So there's all these interesting interactions that start to show up when you start hosting operating systems. But it is the wave of the future. It's the wave of the present, really. Okay, other details we'll just go over really quickly. They are used in a lot of different contexts. The context clearly dictates what the OS needs to be good at. If I have a server system, I need to be really good at I/O. Maybe computation. I don't care about a GUI, so I don't need to do that kind of thing. Personal computers, well, I need to have a GUI, and it needs to be responsive, and so what if I waste some cycles being responsive that I could have used for computing? User interaction is most important, otherwise people are known to chuck computers across rooms and out of windows, so we need to try to avoid that. Let's see, you have mobile devices and tablets. New concerns. I'd like to be interactive, but I have limited energy, so I need to manage my battery life really carefully. Okay, and then of course I can install whatever application I want, so there's all kinds of interesting issues with that. And then connectivity may or may not remain, so I need to think about those issues as well. Let's see, what else? Embedded computers, you can read about that. We won't spend too much time talking about that. The last thing that I want to mention is real-time operating systems, because you hear this term a lot. Real-time operating systems means scheduling is really important. I have to have things done by a specific deadline. Most of the time when you see real-time support in operating systems, it is in a general purpose operating system, and the real-time support is soft real-time. We call it soft real-time because it's not a failure if the OS meets, or I should say, if the OS fails to meet the deadline. That's not a failure. Okay? My kitten video gets stuttery, my music gets stuttery. I'm upset, but it's not the end of the world. The OS didn't crash. If you have a system where those scheduling deadlines must be met, and if they're not met, then it is considered a failure, then that is a hard real-time system. Okay? And it's an interesting exercise to think about what would be hard real-time OSs, but a really simple example is the automobile manufacturing assembly line. Because I've got the skeletons of these cars moving on conveyors, and then I've got these big robot arms which come in with their big welder and go bzz, bzz, and they make various welds. If I go and I try to make a weld and there's no car there, I have a problem. Or if the wrong part of the car is there, I have a problem. Those systems, it's a hard real-time requirement. And if I fail, then the entire assembly line needs to be shut down so that I can go and reset things, figure out what in the world caused this to go wrong. Okay? Any questions? All right, I think that's about all the overview that we have for today. So next time what we're going to do is start talking about the various facilities and OSs, and make sure you enroll in Moodle and make sure that you get your team survey to me ASAP so that I can go ahead and get that all sorted out.